Okay, so the plan for today is to start and finish new section about injective and projective objects. But the first definition will be a little bit more general. So suppose we have two abelian categories. So let A and B be abelian categories. And suppose we have a functor f from category A to the category B. Then this functor f is called left exact. And there is a notation for this. I'm going to write that L is in the lex AB. If we have the following property, so if we have a short on the left exact sequence, so if for any exact sequence like this, the sequence that you obtain by applying functor f is still exact. So that's the definition of a left exact property. So equivalently, you can say that if you look at this thing, you can say that x prime is the kernel of the next map. So this functor preserves kernels. Of course, there is a dual definition for the right exact functor. Let me just, for shortness, just write this in terms of the notation. So f is in the rex, meaning right exact between A and B. Now, if we have a dual condition, so I start with the exact sequence which is only exact on the right, then apply functor f and still get an exact sequence. So in other words, in this case, f preserves co-kernels. Three. Now f is exact if it is left and also right exact. Okay, so a few remarks before the next definition. So sometimes it's useful to know how to say that a contravariant functor is exact. So before it was a covariant functor, now let's take a contravariant functor. I want to say that this is left exact. So is left exact. Well, the condition is the following, and you can see that it's quite actually a natural condition. So I start with exact short right exact sequence, apply functor f, so then f is contravariant, so I map all the errors in the other direction and claim that this is exact. So for any short sequence exact on the right, we have short sequence exact on the left. And it will be important because there is one quite important left exact functor, namely the functor h with the upper x. That's a contravariant functor, and that's an example of left exact functor. 2. Of course, you can dualize this and say what's the right exact functor and do this as an exercise. Now, remark 2 is the following. If I take lex or x, well, I don't know, for x there is the same statement, then this is in the A and B in parentheses. So do you still remember our notation? So in two categories, two abelian categories in parentheses means that we consider additive functors. So here I claim that left exact functor is automatically additive. So don't require this in the definition. This can be checked as an easy exercise. So exercise. In the first remark, this is not a claim. This is kind of continuation of the definition. I want to say when a contravariant functor is left exact. So the condition is this one. So this is exact on the right, but when you apply f, you get exactness on the left.
It means that it is additive map of abelian groups.
Yeah, that's one of the way to say this. Another way would be that it preserves finite products, coproducts, byproducts. Okay, so remark 3, any continuous functor is exact. Is left exact. Yeah, and co-continuous is right exact. No, that's a kind of trivial remark, right? If you all additive functors. So, what's a continuous functor? Well, for example, continuous functor preserve all equalizers, right? And it means that preserves kernels. So it is left exact just by definition. So in fact, you can see that continuous and co-continuous is much stronger requirements. They also have preserve some infinite products or infinite coproducts. So hence we get the following remark. So if we have adjoint functors, then left adjoint is right exact, and right adjoint is the left exact. That is because by the general theorem we know that any left adjoint preserve the colimits and the right adjoint preserves the limits. So for example, we can notice that when you have a bimodule, so B is an RS bimodule, then we have an adjoint pair of two functors. So here we have tensor product with B, and the right adjoint is the home with B. So we can see that tensor product with B, well, that is the left adjoint, and the left adjoint, left adjoint is right exact. So tensor product is a bimodule is automatically right exact, and the home with the bimodule is left exact. Okay, so definition, the main definition of today's lecture. So an object, say X, in the abelian category A, is called projective if the functor h sub x is exact, and injective if h upper x is exact. So notice that these two functors are automatically left exact. So the non-trivial requirement is they are additionally right exact.
Right, where we fix x, in which case?
Well, we proved even more when we discussed kind of preserving the limits. We proved that, for example, this functor, h with a lower x, actually not just exact, left exact, meaning that it preserves kernels. It's actually a continuous functor. It preserves all limits. We also proved this, that was a corollary, and the idea was to just go to the dual category. So this kind of, if you know this statement, this is just going to the opposite category. It's nothing new here. Okay. So first proposition, there are several other ways to characterize, say, injective objects. Of course, there is a dual statement for the projective objects. So take X, an object in the abelian category A. Then the following are equivalent. So first, X is injective. Second, now we have the following property. If you have a monomorphism, let me draw a commutative diagram for this. So this is a monomorphism. Some y prime is a subobject in the y. And I have a map, say f, to this object x. So then, well, let's call this map maybe I. So then there is an extension f tilde. So sometimes this is used as the main definition of an injective object. So any map from the subobject you can extend to the whole object if the target of this map is an injective object. So of course here I assume that when I do this extension I'll get a commutative triangle. So condition 3 is the following. Any short exact sequence okay. So x, y double prime. So we take any short exact sequence such that the first term is this x. So then this splits. Okay, so proof. Well, first we prove that 1 is equivalent to 2, and this is kind of more or less tautological. Well, you have this sub-object and the object y, so let's extend this to a short exact sequence by taking the quotient by the sub-object. Well then, if I apply functor h, so from the definition I need to take the h with the upper x, so this is a contravariant functor, I'll get the following. So let me maybe write this in terms of the Holmes, it will be easier to understand. So and for Holmes I just use short notation with a. So I'll get a, so here I have y modulo y prime is mapped to the x, then this I have y mapped to the x, and finally I have y prime. So this part I'll get automatically because of the left exactness of the hx. All right? So then the claim that this is injective exactly means that this last map is in this case just a surjective map of abelian groups. Right? But surjectivity of this last map is precisely this statement that we have in 2. Right? We start with some map f from the y prime to the x, and what is this map here? So if I have a map from the y to the x, right? Then I just take composition with I, and I'll get map from the y prime to the x. So this map is just the composition with I. So if I start with any map f, and I can present this as some f tilde composition with I, this is precisely the pre-image of this f. So that's 1 and 2 are equivalent.
it's one from two and
Together. Okay, let's go from 2 to 3. And this is probably the easiest part. Well, we have the short exact sequence. Apply functor hx to this thing. And so without this 0, this is automatic. So the question is when I can claim that there is an exactness here. So exactness here that I can add 0 here is exactly condition 1. And exactness here is the same condition as this map being surjective. But this map being surjective is precisely condition 2.
and all exact sequences are of such kind. We use it.
I don't understand the question. No.
Что y'.
Yeah, here, just any short exact sequence, what's important that the first term is x. For injective object, this always splits. Okay, from 2 to 3, well, I want to show that any short exact sequence splits. Well, I take the short exact sequence. Now, x is the subobject, and I can take the identity map on the x.
I'm sorry, if x and y are fixed, isn't it true that y double prime is up to init up to isonorm?
Sure, yeah.
So it's not like just some y, it's just kernel. Not kernel, but like,
Any short exact sequence such that the first term is injective.
yeah.
So that's the same condition. So you won't convince me otherwise. So let's take the identity map. So the identity map can be lifted from the subobject x to object y. But the commutativity of this triangle precisely means that R is the retraction of this map. Hence this short exact sequence splits. So finally, from 3 to 2, yeah, from 3 to 2. So let's take y prime subobject in the y. So let's take map to the x, call this map f. So I want to show, so I know now 3, I know that any such short exact sequence splits. I want to show that there is a lift of this f to the y, right? Well, I'll take the push out for this diagram,
What is R again?
the extension. Well, in the 2, we assume that for any map, there is an extension from a subobject to the object. So let's call this R. That for reason for you know this R because this is the retraction for this map. And if there is a retraction, short exact sequence splits. Okay. So let's take a push out for this diagram. So this will be x, push out over y prime with a y. So here I denote maps f prime. If this was I, and this low map is I prime. Now if you apply lemma 1, you're going to see that I prime is a monomorphism. Hence, by the assumption 3, there is a splitting here. So let's call this R. So we know that the R I prime is the identity map. Now, if you just look at the composition of the R, F prime, and I, well, using that this square is commutative, I can rewrite this as an R I prime F. Now, R I prime is identity, so this is F. So we see that this composition, namely this map and this map, is the retraction for the I.
Sorry, R is.
So it's not the retraction, so just the map that goes in the other direction.
What is R?
Well, the retraction that we have here.
And lemma 1 is something about that we can replace.
The lemma 1 saying that if this is a monomorphism, then this is a monomorphism.
That.
Yeah. Lemma 1 from the diagram lemmas.
Okay.
So we start with some sub-object, right? Take the push out. In this push out, I prime is a monomorphism. So it means that I can, if I want, I can continue this to the short exact sequence, and the short exact sequence splits, right? Because this is the assumption 3. So any short exact sequence where I have x in the beginning splits. So in particular, it has this retraction R. So from 3, I'll get the existence of this R. And then there's just a simple computation with 2 lines to see that if you actually go like this, and like this, you still get map F. So this is what you want to construct, right? So this thing is the F. We can call this that this is F tilde.
When we used condition free, what R exists?
Yep.
That for which sequence?
Well, the sequence I just don't want to write because we don't really need it. The sequence would be the next term. You take this thing and take a quotient by x. That's the sequence. Okay. So next proposition. So let xi be a set of objects in the category A. Then the product is injective if and only if each object is injective. So injective, and this is for any I. So let's say that I is in the set large I. Okay. So let's go first in one direction. So we assume that all these objects are injectives. We want to show that the product is injective.
We assume that A is small.
Yeah, we assume that everything makes sense, so that we can take products. So what's called A, B, 3 star. So let's say that we have a map F to the product, and I want to show that I can leave this map from this sub-object to the object Y. Well, here from the product I have projections Pi to the Xi, and then for this composition, since Xi is injective, I know that there is a lift. So let's call this lift Fi. Now, if I want to define a map from an object to the product, I need to specify all its components, namely this. Well, what happens if I take this composition? Well, take this projection and this map. So this uniquely defines a map F tilde. Okay. Now let's go in the other direction. So now we assume that the product is injective. So let's say that we have sub-object Y prime in the Y, some map F to the Xi. So let's define large F to be a map from the Y prime to the product. Right, again, to specify a map from an object to the product, I need to specify what happens when you take the compositions with projections. So projection Pj, the composition with the map large F, is defined as follows. This is map little f if I is equal to j and 0 in all other cases. Sorry, I is equal to j and I is not equal to j. So there is a unique map like this. And then for this map, so one more diagram. This is a map to the product. So here I have large F. Here I'll get an extension. And still there is a projection Pi to the xi. Well, for the F tilde, I just take this map.
Is it true that the product of functors is active only if all the functors are exact?
I think it's true, but it requires a separate proof. Yeah, definitely I thought in that direction. I think this proof is easier without functors. Okay, so that was kind of two more or less trivial observations about injective objects. Well, of course, we can dualize everything and talk about the statements for the projective objects. Well, let's say that P in the A is projective. Well, what would be the equivalent condition 2 in the proposition that we proved in the beginning? Well, the condition would be something like this. You have x, there is an epimorphism to the x double prime. So here you have projective object, there is a map here, and then you can kind of leave this map. So again, if this is, say, let's call this G, and this is G tilde. By the way, about terminology, so in this case, I think the lift of the map is kind of the correct terminology, but in the case of the injectives, because you can extend this from the sub-object to the object, the extension would be the correct terminology. Okay, so that's just dual condition. I want to formulate it to avoid any confusion. So, and of course, the condition 3 would be the following. If you have some object x that is mapped to the object x prime mapped to the x, and the last term in the short exact sequence is p, then this splits if and only if p is projective. You can dualize the proofs, or you can say that you go to the opposite category, and projective in the opposite category is injective in the category. So of course the dual statement for this statement would be a statement that if you have a family of objects, the coproduct is projective if and only if.
Splits for it.
Hmm?
Splits for it.
Yeah, any short exact sequence such that the last term is projective splits. Or if any such sequence splits, this object is projective. Well, for projective objects, actually, there are easy examples. Say, if you take your category to be the category of the left modules. Yeah, of course, by definition, projective modules are projective objects in this category. But for example, if you just look here, you can see that every free module is projective. Since, well, if you kind of replace this by the Ri, this map is completely determined by where you send the generators. So you just choose any pre-image of all the images of the generators, and thus you define a map here. So any free module is projective. And we can say even more. If you take a projective module, well, you can always find a surjective map from the free module, right? We just choose the generators in the P and generate a free module by this set of generators. So then this epimorphism has some kernel. And since this P is projective, this thing splits. So we can see that any projective module is automatically a direct summand of a free module. And dually, if you have two projective modules, then the sum is also a projective module. So a module is projective if and only if it is a direct summand of a free module. P, PP is a summand of a free module. It's not a sum, it's a summand, because this thing splits. So this thing is just isomorphic to the sum of these two pieces. And
why if P plus K is P plus could you repeat the statement?
well, the first observation was that if I have a projective module, this is necessarily a direct summand of a free module. And the second observation was if you have any direct summand of any projective module, this is also projective.
Well, it's essentially the last proposition proved, right?
Yeah. Well, for injectives, the
Dually.
yeah, the dual version of the last proposition, yes. Okay. So finally, a non-trivial theorem. And for this non-trivial theorem, I see that I need another definition.
But K maybe not projective.
K is projective. This is again a direct summand of a projective module.
I can just replace K and P, right?
Yeah. K is projective, yes. So because any direct summand of any projective module is projective, that is a duo of the second proposition that we proved for injective modules. Okay, so I need a definition for the next theorem. So definition, growth in the category is an AB5 category with a generator. And as we're going to see even today, a lot of theorems for abelian categories are proved in the assumption that the category is authentic.
I forgot, what is the condition?
No, we had several equivalent conditions. For example, we can say that the direct limits are exact. Well, the generator, if you have any two objects and any two maps such that these two maps are distinct, then from a generator you have a map H such that the composition HF is different, no, the other way around, so GH. So that's the definition of a generator. Okay, so let A be a Grothendieck category. So with generator G, an object I is injective if and only if, well, for any sub-object Y in the generator and any map, say phi, to the object I. So for any Y and phi, there is phi tilde. So in other words, I'm saying that we can solve the standard extending problem, but not for any object and sub-object, just for the generator and some sub-object of the generator. So it's, if you know this theorem, it's much less conditions to check if you want to show that something is injective. Proof. So of course in one direction this is clear. So if you know this for all subobjects of all objects, we know this for subobjects of the generator. So the non-trivial part is in the other direction. So let me take subobject x prime in the x, and phi will be a map from the x prime to the object I. So I want to show that there is an extension. So let M be the PO set of all the possible extensions. So x double prime, phi double prime. So here I have x prime, which is subobject in the x double prime. So suppose I already have an extension, say f prime to the I, and then this extension f double prime forms a commutative triangle.
What is poset?
Partially ordered set. Chum. Right, so this is not empty because we already have at least one element, well, x prime, and the map phi. Okay, so of course I want to apply the Zorn's lemma. So this kind of standard proof. So I want to show that any chain has an upper bound. So if I take a chain, so for a chain I can take a sum of all such objects. Well, this sum will be isomorphic to the direct limit, and the direct limit has canonical coprojections. So hence, if I want to kind of extend this phi double prime to the sum, well, here I already have phi double prime I, right? So these maps are given. Now a map from the direct limit, which is a co-limit, is completely determined by these components. Hence, there is this map. So phi double prime with the qi is the phi I double prime. So this formula uniquely determines the map phi double prime. So any chain has an upper bound. By Zorn's lemma, there is a maximal element in the M. Ooh. Here, you mean here and here?
Yep.
Well, here just an indication of the kind of objects I consider. I just call the kind of elements in this poset x with a double prime and the map with a double prime. So here I've used double prime for the individual objects, and I extend this to the sum.
Okay.
So it's kind of morally the same. So by Zorn's lemma, there is maximal element. So let's call this x tilde phi tilde. Of course, I want to show that this x tilde coincide with the x, right? So if I can do this, I'm done, right? So then I extend it from the sub-object to the whole object x. So if this is not the case, then I'll get two maps from the x to the quotient of the x by x tilde, well, namely the canonical projection and the zero map. Then, by the definition of a generator, there is a map H such that in this case composition of the pi and H is not equal to zero.
Side double prime are subobjects of x.
Yes, yes. So these are all subobjects.
And the sum O is one subobject.
Hmm?
And the sum is also subobject.
Yeah, sum is also subobject by the definition of sum. Okay, so I have these two maps, the canonical projection to the quotient and the zero map. So composition with H supposed to distinguish these two maps. So composition PH is not equal to 0. Then from this we can see that image of the H is not contained in the X tilde. So that's not a sub-object, because otherwise you'll get the zero map. So then we do the following. So let's take G. Then there is a map, not surjective, but epimorphism to the image, right? So then this map has some kernel K. So this is the beginning of the diagram. Now, here I can take the image of H and take the intersection with the X tilde. This will be some object in the image. And take pullback for this diagram. So the pullback give me H inverse of the X tilde. And since this is epimorphism, I can claim that the kernels are also isomorphic. Okay, and somewhere here I have object I. Well, what we know? We know that there is a map from the X tilde to the I. Right? In particular, you can restrict this map to this intersection. This gives you a map like this. So you look at the composition of the H inverse of the X tilde, and this map, you still get the map to I. Now, this is a sub-object in the G. So we can extend this Sorry, what?
How do we define the restriction map?
What restriction map?
You said restriction map.
Restriction is just the composition. If you want to restrict to a sub-object, it's just the composition of the embedding of the sub-object and the given map.
Yeah, wait. What is the map between H and image intersection with X? It's kind of both sides? Or what?
No, you have a map from the X tilde to the I, right? You can restrict this to the sub-object of the X tilde.
Okay.
Yeah, and then you take composition and you get a map from this object to the I.
Okay.
Right? And now, by our assumption, we know that there is an extension from the sub-object of a generator to the generator. So there is no big picture because we have this thing. Okay? So by this condition, we have the blue map. And finally, what happens if I take this blue map and restrict this blue map to the K? Well, that would be, if I go on like this, that would be the same as going like this, which is clearly 0. Hence, there is a green map from the image to the I.
I'm sorry, first, why is it the same, then why it's clearly 0?
So what's the same?
Why are these two ways? I believe from the lower row, right, and up.
Why these two things are the same?
No, this is just by definition.
By lemma.
Yeah.
Yeah, so again, I have a map on the X tilde, so I have a map on the sub-object. So I take this composition here, so I can extend this to the G by this assumption. So then I look at this map from the G to the I. So I can go like this, right, with the blue line. But that would be the same if I go from K and use the upper part of the diagram. Go from K to here, and then to the I. But this composition is 0. Hence, the map from the G to the I is 0. So actually, this map is defined on the quotient by the kernel, which is this co-kernel. And this is the last map, the green map. So let's call this last map G tilde.
Contradiction. Because we see
No, not yet.
image of H is larger than.
Well, I think we need just one, maybe two more lines to derive a contradiction. So we constructed this map G. Well, why I call this G tilde? Let's call this just G. So by the way we constructed this, we can see that the G restricted to the image of H intersect with the X tilde is the same as the phi tilde restricted to the image of H intersection with the X tilde. Well, because essentially every triangle that you see on this diagram is a commutative triangle. So when you restrict these two maps here and this map here, they are the same map by construction. So if they coincide on the intersection, well, I look at the short exact sequence where image intersect with the X tilde sits inside the image plus X tilde
Where is it?
image plus.
Where is it?
It was constructed here by Dorn's lemma. And this is also kind of phi tilde restricted to this object. Oh, this map, the red map, is phi tilde restricted to this intersection. Okay, so we'll look at the short exact sequence. Now, if we look at the map, say G with two components, G and minus phi tilde. Right, so this map on the intersection, this is 0. So hence this is not a map from this thing, but this is a map from this thing. So we extended our map phi tilde to even larger object, which is X tilde with the image of H. And that's a contradiction.
Could you repeat?
Because that was maximal element. And we constructed even element which is even larger in this poset.
Сейчас. То есть мы определили какие-то предположения, как это предположение связано с теоремой?
Well, I wanted to show that this thing that I constructed X tilde actually coincides with the X. Because if this is the case, I'm done with the proof. I extended from the sub-object to the object X, because I already extended to the X tilde. And so I assume that they are different, and hence I can construct these two different maps. So the assumption that X doesn't coincide with the X tilde give me the non-trivial map pi, and everything follows from the non-triviality of the map pi.
Could you repeat one last construction?
Yeah, so here on this sum, if I want to define a map on the sum, right, I can just specify two components. So I take components G and minus phi tilde. Then the restriction of this map to the intersection is 0. That's precisely the previous line. Hence, if the restriction on this subobject is 0, actually the map is defined on the quotient by this subobject. And so we're able to construct our extension from the X tilde to the X tilde plus the image of H, which is a contradiction. By the,
We use chains in sub-objects of
Yep.
X.
yes. Hmm? Well, again, this was one of the lemmas that we proved last time.
I think this is AB for AB5 categories,
This thing.
or AB4. I don't know.
That maybe to some.
Yeah, so
I remember AB5 was something about two statements, very weird, that we have some intersection.
yeah, that's kind of weak statement.
Yeah.
Yeah, then there was a statement about the exactness of the directed limits, and from the exactness of the directed limits, we will get this isomorphism, because this will be always an image of this map, and by the AB5 condition, there is no kernel.
Прошу прощения, а почему x tilde равно x, следовательно, и imb tilde?
Well, because we start with the map on the sub-object, and we wanted to extend this to the object X.
And the fact that by drawing motion by intersection is the sum of definition, right?
It's more or less definition of the sum of two objects. Yeah, I actually proved this already when we discussed, for example, the what was second isomorphism theorem.
Yeah, I was thinking about it.
Okay. Yeah, for example, this theorem, when you consider A to be a category of the left modules, then you get the following. So if you have an ideal, so let's call this ideal J, that sits inside the ring, right? So this is ideal. Then, if you want to check that the module is injective, it would be enough to extend from an ideal to the ring. This just follows from the fact that the ring is a generator. An obvious one. And this is called Bayer's criterion.
R as a generator as a R module, right?
Yeah, so R as an object in this category is a generator.
Yeah, I think we
Yeah.
Who's here?
It's B-A-E-R. Bayer's, I think. So this would be just a special example of this theorem. And the dual statement doesn't exist. Well, what you mean dual statement for modules?
No, not for modules in general. So we would have to study all like covers of cogenerator.
Yeah. So you need to assume that you have a category which is AB5 star with a cogenerator, and then you get this corresponding result for the projective modules. Yes.
But it's kind of.
But
Yeah,
for
it seems impossible to study all surjections onto a given object, right?
well, it's not possible. Well, it's definitely possible. You take the category that we discussed just in this theorem and take the opposite of this category. There are no problems. But the point I was making that this doesn't exist. For example, if you take the category of R modules, this is not an AB5 star. So there won't be a dual statement for the modules. Yep.
Where did we use that it was 85?
For example, when we discussed the sum and the limit, that they are the same. Okay, so another definition. A category has enough injectives if any object X has monomorphism from the X to the I, where I is injective. This is kind of the beginning of the homological algebra, because if you want to study some objects, well, you embed X into an injective object, there is some kernel, you take the kernel, embed this in another injective object, and do this as many times as you need, and you get an injective resolution. And this is the main way to derive functors. So, for example, it's quite useful to know that your category has enough injectives. And here I have one easy preliminary proposition with two parts. So on the first part, if category A has injective cogenerator, then A has enough injectives. This is easy part. And the second part, if A is AB3 star, which just means that we have products with a generator, and has enough injectives, then A has injective cogenerator.
This is not true for our
Well, our modules definitely satisfy all the conditions. Hmm?
Sorry, what's the cogenerator for modules?
Well, the cogenerator in the category of the R mod will be the following. You take the hom over Z, R, Q modulo Z. So that's a cogenerator. Now for the proof. So first part, or if it has, well, the statement is not completely correct. If A has injective cogenerator, right, then it has enough injectives. And the converse, if you have enough injectives with some technical assumptions, then you have injective cogenerator. So the first part is trivial, because if you take an object, you can always embed this. Well, let's give this cogenerator name Q. You can always embed this into some power of the Q. And this is injective by the second proposition of today's lecture. So the
Power is a
product.
set of all morphisms from X to Q.
No, this is just a product over all little s and the s of the Q.
S, the set of all morphisms.
Ah, yeah, well, that was what we used in the proof, but
But probably it would be
yeah, it might be, in example, it might be smaller set. So this is proof in that one direction. In the other direction, it's a little bit more interesting. Well, I take the product of all objects where objects are quotient object of a generator.
First part one, what is this?
This is the proof. Because the observation is so simple. You see, I'm assuming that they have an injective cogenerator. Then they have enough injectives. But one of the theorems that we proved about cogenerators that has the property that any object is a sub-object of some sufficiently high power of a cogenerator. So now, since Q is injective, everything follows immediately by the proposition that we proved earlier. Now, let's take this product. So Q of S, these are all quotients of the generator.
Why is there a set of?
Oh, that's a good question. Why this is a set?
How different code from G?
Well, the Q of any object, say any T, this is just all quotient objects. So this we have, say, X, set of X, such that T t is mapped to the x, and this is an epimorphism, all the quotients of the given object. So the question is why this is a set. How we can prove that this thing is a set. Well, in the abelian category, there is a bijection between the set of subobjects and the quotient objects, because for a quotient you can take a kernel, for a subobject you can take a co-kernel. And why the set of subobject is, well, why a class of subobjects is a set.
What is square of J?
Hmm?
What is called J?
Class of all quotient objects of an object G. I wrote it here.
What is object G? Generate? Cogenerate?
G is a generator. Yeah, so with the generator G. And has enough injectives then.
Можно все-таки определение, что такое когенератор?
Take the definition for generator and go to the opposite category.
Sorry, question about one. We know that subobject of injective is object.
No, this is something that we don't need here. Here we have an assumption that we have a category A, which is,
Sorry.
so we know that we have AB3 star, meaning that we have all small products, right? So product has to be over a set. It's not obvious that this thing is a set.
And we know that product, so inject, let's say product which is to injective objects is also injective. Right?
Yeah, that we proved earlier today, yes. But at the moment, F is not injective. It doesn't play any role at all. I'm just asking why this product exists in this category. In other words, why this class is a set.
So we don't really know
Yeah.
what exists.
Well, really easy answer, by electrification.
By what?
Electrification.
What?
What?
A category with a generator is well powered. And we proved this when we discussed generators. So
I forgot what is
there was a theorem, remember in that case there was no abelian categories, so I stated all the conditions that I need. I stated that I have a category with a generator which is balanced, that has finite intersections, then this category is well balanced. But for abelian categories, because any abelian is balanced and have finite intersections, the statement is much easier, so this is called the rectification theorem. If you have a generator, the category is well powered. Yeah, so this we proved. So this is a set, this product makes sense, and I can embed this into an injective object, right? Since I assume that I have enough injectives in this category. So actually I claim that this I is in fact an injective cogenerator. Mm-hmm. So let's show that this is a cogenerator. Well, the fact that this is injective object is by the construction, so we only need to show this I is actually cogenerator. So let's take a map between two objects, say F, right? So first of all, since we have a generator, we can find the map H from the generator to the X such that the composition of the F and H is not equal to 0. Well, this is the definition of a generator, which is G in this case. Now, of course, well, before we discussed about, well, we discussed generators, cogenerators for the two arrows, but in the abelian case, the second arrow is always 0. You can always do this. So let's take this composition and decompose this into the image. So take the image, then there is a surjective, well, epimorphism on the image, and the image is a sub-object in the Y. That's we know that we can do in any abelian category. Okay. So what we can notice that this image of this map is a quotient object of the generator G. And hence, I can embed this in I, right? Since all products of all quotients are embedded into I. Well, I is injective. This thing is a sub-object of Y. So I can extend this. I want to call this map G. And then G F H is not equal to 0.
How then do we get G?
Well, this is a sub-object of the object, and this is injective. By the definition, one of the equivalent conditions for an object being injective. So this is the extension property for this sub-object and this object. So there is this map G, and the composition of the H, F, and G is not equal to 0.
Why does there exist map from image to I?
Well, because this image is a quotient object.
Well, yeah.
And then, well, this is just will be one of the factors in this product.
Yeah, but this is a product, not a sum. How do we get a map?
Well, take a product, right? So then there is a projection to the F, right? So we have map to the I.
Maybe it should be a sum.
Nectar AB free star.
Yeah, for this sum, this would work. Yeah, I don't think that it is possible to extend this map. So probably you're right. I think we need to we need to reprove this star and replace the products by the co-products. Yeah, then there is no map. There is no problem with this map to the I. Okay. So I was claiming that the composition of the G, F, and H is not equal to 0. Right? Well, that is, well, this is the composition. And since we have all these two commutative triangles, well, we can go kind of in a different way and see that this is not 0. So if you go, for example, I don't know what would be. Yeah, for example, go here, and this is non-zero map. So here, this is a non-zero map. Well, if this is 0, since this is a monomorphism, this has to be 0, but this is not a 0 map. So this is not 0. Yes. Yeah, so okay, so this composition is not equal to 0, and then I claim that the composition of the G and F is not equal to 0. G and F not equal. Well, this is because, well,
Is that composition with 0 always?
yes, well, that's the argument. If this is 0, then definitely this is 0, so there is no need to think about this. Yeah, and that's what we want, right? We constructed the map, well, we take any non-zero map between any two objects and we constructed a map to the cogenerator such that the composition is not zero. Hence, this is indeed a cogenerator. Okay, next definition.
Now, if my eye is cogenerator, we need two maps.
The second map is zero. In that,
And we need to check it only for zero because it's.
yeah, in that Abelian case, we can always take the second map to be zero. So let's take a monomorphism from x to y, and this is called essential. Or sometimes it's also called, well, essential monomorphism or essential extension, or just for shortness, EE. If we have the following property, so for any sub-object y prime sitting in the y, the intersection of the x and y prime is not zero. So, of course, for any non-zero sub-object. And 2, an injective hull or injective envelope of x is an essential extension such that I is injective. No, something like the smallest possible monomorphism.
Shouldn't it be like the largest because it intersects with any other?
Because if it's small, we can.
Well, that depends on how you look at things. What you want, what you consider fixed, the second object or the first object?
Second.
Well, I consider it to be fixed the first object, because essentially what I want to do with this, I mostly will be interested in the second part of the definition. So I can always embed, well, I have enough injectives, I can always embed this into injective, but I want to do this in the smallest possible way. So then I can start construct the smallest injective resolution, the minimal injective resolution. Okay. So in the next proposition, I want to summarize trivial properties of this definition. So in the first part, if we have two monomorphisms, so if f from x to y and g, which is a map from y to z, are two monomorphisms, then the composition gf is essential if and only if f and g are essential. So second part, so if we have an essential extension f and an injective object I, and suppose that in this case, well, again, I want to draw this in terms of diagrams. So we have x sub-object in the y, and this is essential extension. And suppose that this x is embedded into some injective object. Well, then I can extend this to the y. I know this automatically since this is injective, but when I do this extension, I still get a monomorphism. So this is phi tilde, So this diagram is commutative and phi tilde is mono. And 3. That's the claim of the proposition. I don't prove anything yet, I'm just formulating the statement. So n injective how is unique up to isomorphism. So this is 3 properties that we need to show. Well, I think the first one is more or less trivial, right? Well, perhaps there are even shorter way to think about this, but I think it like this. I take this composition of 2 maps, right? So if I have a sub-object z prime, I take pullback, I'll get the intersection. I take the second pullback, and I'll get the intersection of all 3 of them.
Condition here. We fix I. Or
Well, you can say that for any injective object such that there is a monomorphism from x to the I, there is an extension which is also a monomorphism.
Okay, and the whole in general is just an injective map from some object to, right? Or what?
Well, the whole is essentially essential monomorphism from an object to an injective object.
Well,
Yeah.
it needs to be essential.
Yeah, I wrote EE here. This stands for essential extension.
what means that it is unique up to isomorphism?
It means that if you compute one and the other, there is an isomorphism between them.
2 different ways.
No, we fix x.
For x, right? So the standard notation for the injective how is the, well, you take x, suppose you can take I and I prime, both satisfying these conditions. These are essential extensions, and I and I prime are injectives. So then I claim that actually these 2 things are isomorphic, and the notation for this, for the injective how of an object, is usually E of x. So this is notation for injective how of x. Yeah, by the way, terminology is kind of different in category theory and in algebra. In algebra, the things are usually called injective house. In category theory, this is injective envelopes.
And why is there an e?
Ну, потому что я была.
Yeah, I think that's the answer. Yeah, back to the proof of the first statement. So do you agree that we have such pullbacks? So then, for example, if we know that the composition, well, what we know, for example, if we know that F and G are essential monomorphisms, then this is non-zero by first pullback, this is non-zero, then this is non-zero by the second pullback. So the composition is again essential monomorphism. So in one direction this is trivial. Now in the, so clearly if F and G are essential extensions, then the composition is essential extension. So this part is easy. Now, how about the other direction? Suppose I know that the composition, so suppose composition is the essential extension. Well, I think it's easy to see that G is essential extension, right? Because, well, if I take non-zero z prime, if the intersection with y is 0, well, then definitely this last intersection is also 0. Hence, this cannot be, so the composition cannot be essential extension. So again, this immediately implies that G is essential extension. So maybe the only part that requires some computation or maybe some observations is that F is essential extension. So let's rewrite this diagram. Take some sub-object y prime. Okay. But now I can do the following. Well, f and g are monomorphisms, so in other words, y is a subobject in z, y prime is a subobject in y, so I can consider y prime as a subobject in the z again. And if I take this pullback, I'll take the intersection of y and y prime and still get y prime. So then,
Почему же?
well, take non-zero z prime here. Suppose this is not essential extension, so then this intersection is 0. But then this intersection is 0. But if this is pullback and this is pullback, the rectangle is also a pullback. Okay. Well, do you agree that with this observation everything is done? That the G is essential extension? Well, because well, from this subobject, you can consider this as a subobject in the Z and apply the same argument as before. So this is pullback, this is pullback, the rectangle is pullback.
He will put that F as the section.
Yeah, so that F is well, for G, this is easy. We've done this already.
And for F,
Well, because well, you want to compute this intersection, and you want to convince yourself if this is not 0, then this intersection is not 0. Now I can consider y prime as a subobject in Z. This pullback of the y prime and y over Z give me y prime. So this pullback is what I want, but I can also notice that this rectangle is a pullback. So this I know that this is not 0. This whole composition is essential extension, so this is not 0.
And we know that Y is a subobject of Z, right?
Yeah, so these are two monomorphisms, so they are subobjects. Okay, proof of the part 2. So I have X, which is subobject in the Y, and this is essential monomorphism. So I assume that I can embed this into some injective object, call this map phi. So I know that this extension phi tilde exists because I is injective. So let's say that the K is the kernel of the phi tilde. So some subobject here in the Y, right? So if I can show that K is 0, then I'm done. Well, but look at this diagram, take the pullback. The pullback give me the intersection of the X and K. Now, the map from the intersection to the I, what is this? Well, if you go like this, it's 0. Yeah, so this map from the intersection to the I, this is a 0 map. Yeah, so now since phi is a monomorphism, so phi is mono, we can say that the intersection is 0. But if this intersection is 0, well, F is the essential extension, tell us that K is 0. And we proved part 2 with this observation, right? So 3. We want to show that injective hull is unique. Well, suppose we have two embeddings into two injective objects, and these two maps are essential extensions. Now, by using property 2, since this is an essential extension and this is a monomorphism to an injective object, I can extend this map and still get a monomorphism. Right? But if I do this, then I prime is the sum of I, well, some complement, say C, right? Because this corresponding short exact sequence splits. If I take a quotient of the I prime by the I, this splits, and
We get monomorphism
here by 2. This is the essential extension. This is a monomorphism to the injective. So then, since this I prime is just a direct sum, if I want the map from the x to the I prime, which factors to the I to be essential extension, I need C to be equal to 0.
It splits it. It was.
Because this is a map from an injective object.
But I prime is also injective object, right?
Yep.
So you can consider the opposite. Arrow.
You could, but that's not the way I'm trying to prove it.
But if you have two monomorphisms, then you return.
No, it's not.
Well, there was example on the week ago on the break. You embed z into z by 2, embed z into z by 2. Yeah, but here we're almost done with the proof. We have this splitting of the I prime, and if I look at the map from the x to the I prime, I constructed a subobject, namely C, such that it intersects with I by the 0. Right? And x lives inside I, so it intersects with x by 0. So C is 0, and I is isomorphic to I prime. Okay, let's take a break.
Sorry, why I prime is equal to I plus?
Well, this is an injective object. I have a monomorphism to some other object, so I get a quotient, I get a short exact sequence, and the first object in the short exact sequence is I, so it splits.
So you just called it.
Yeah, well, because the argument is so elementary, sometimes if I just take injective object, embed it somewhere, I know that there is a map in the other direction, the retraction. I just don't write the rest of the diagram. Ну вот мы построили под объект C внутри и штрих, да? Такой, который пересекается с x по нулю. Потому что он даже совсем и пересекается по нулю, а x внутри и сидит. Значит, мы теперь используем, что вот это отображение из x в и штрих было существенным мономорфизмом. Так, кто-нибудь еще хочет сдать домашнее задание?
Я понял, что у меня с собой листочек. Я его сейчас допишу.
Записывайте. Ну, может, на прошлом месте сдать. Сейчас это не обязательно. Как хотите.
То есть, ну,
Я
расскажи,
как бы-
куда онлайн присылать такую домашку?
Это на почту, например, мне. Ну, там почта в этом в Google классе есть.
Здесь использовали сегодня вот такой вот
здесь мы доказали, что у нас есть,
И такое.
да, что у нас тут предел, это сумма таких штук, да. А теперь можно просто посмотреть, что на самом деле, что будет в том примере, который, вот, в той задаче, которую мы сейчас решаем, что будут вот эти образы. Эти образы просто все будут.
То есть мы, да, то есть мы здесь считаем f это функтор из, да, то есть это вот это утверждение.
Ну, это вот это утверждение, мне кажется, АБ5 тоже нужно использовать, потому что там у нас еще будет какое утверждение, что, помните, у нас из, ну, вот это утверждение, то, что вы сейчас показали, да, оно дает следующее, оно дает, что у нас есть каноническое отображение как бы из предела суммы вот эту, да, и это будет как бы образ, вот, если мы посмотрим на отображение из предела в объект, соответственно, образ это будет сумма. Ну, мы какое-то такое вычисление где-то там делали, если там посмотреть, там еще где-то
Делали такое.
есть. Да, вот оно вот такое вот, видите?
Да.
Если мы посмотрим, здесь будет образ, это вот сумма вот эта, да?
Да.
Которая сюда вкладывается. Но потенциально здесь еще может быть какое-то ядро, да? То есть вот это отображение, есть какое-то ядро, но его нету, потому что у нас есть АБ5.
То есть это из АБ5 следует, что нет ядра.
Да, потому что АБ5 нам говорит, что если вот это точно, то вот эта штука тоже точная.
Да. Да. Спасибо.
Что у нас дальше будет? Ну, сейчас мы производные функторы определили. Нет?
Я все еще пытаюсь двигаться в направлении теоремы Фрейда Митчелла.
То, что вкладывается.
Да, я думаю, что я не смогу доказать полностью. Вот после этого займет там, лишнее еще, как минимум, занятие другое. Я просто не хочу этого делать.
А что там прям?
Ну,
Инженерия какая-то нужна.
да. Вот, там, в общем, как бы это сводится к такую подзадачу. То есть, например, если у вас есть категория, которая полная и с проективным генератором, то для такой категории вложения довольно легко доказать. Надо просто кольцо, это просто эндоморфизм этого генератора, вложение это просто, соответственно, хомба из генератора. Вот это вот функтор будет вложения. То есть это не очень сложно, и это будет точный функтор, потому что объект проективный. Но возникает вопрос, как произвольную абелевую категорию вложить в какую-то абелевую категорию, которая кополная и обладает проективным генератором. И вот это чуть более сложный вопрос. И, насколько я понимаю, у него есть ровно одно решение. Это искомая категория, это категория Lex из категории Вабелевой группы, точных слева функторов.
И вложение.
Вложение это как и раньше енедовское просто. То есть енедовское, как бы, если вы смотрите просто все, например, функторы аддитивные из категории Вабелевой группы, енедовское вложение, оно будет только точное слева.
Ну да.
А если вы смотрите в Lex, то оно будет точное. Такое вот есть наблюдение. Но это надо доказывать. Вот, то есть, ну, в чем, за что борьба идет? За то, чтобы это вложение из категории абелевой в модуле было точным функтором. То есть, как бы именно это вложение интересно, если какое-то другое, то это неинтересно. Вот, соответственно, нужно точно вкладывать. В модуле вкладывается по инеде. Понятно как, и модуль обладает всеми мысленными хорошими свойствами, которые просто приходят из категории абелевой группы. А для лекса это надо отдельно проводить работу и много чего доказывать.
Что вот вложение будет точно? Или в смысле?
Хотя бы, например, то, что доказать, что лекс это абелевая категория. То есть даже вот это доказать, это уже требует некоторой работы. В общем, я про это некоторое время думал. Я знаю 3 доказательства этого факта. 2 я прочитал, одно я сам придумал. Ни одно из них я не хочу рассказывать. Ну, потому что оно так или иначе очень сильно уводит в сторону. Ну, вот у Фрейда, который прочитал это самое прямолинейное доказательство, оно самое длинное и непонятное, ну, потому что в те времена еще никакой машинерии не было. Альтернативное там, доказательство Гретендика использует сэровские подкатегории и фактор категории. Это чтобы все это описать, построить, нужно еще лекции или 2. Я не очень хочу это делать. И 3-й подход, видимо, самый элементарный, но он, тем не менее, тоже опирается на что-то из теории категории, что мы не успели обсудить, на фильтрованные капределы. Поэтому их надо отдельно рассказать про фильтрованные капределы, тоже не очень хочется делать. Поэтому я, видимо, там сформулирую как бы некоторую общую стратегию и несколько шагов оставлю в качестве упражнения. Вот так. В общем, если разбить на шаги, там понятно, в общем, как в целом это все работает. Но все до конца я доказывать не хочу. Вот, а план такой вот. Я думаю, сегодня закончу инъективные эти объекты, но я не успел довольно много. Поэтому через 2 недели надо закончить инъективные объекты. Я хотел еще поговорить про всякие конечно порожденные, конечно представленные объекты произвольной абелевой категории, ну, абелевой гретендиковой категории. Там довольно забавные свойства. Мне, по крайней мере, очень нравится. Как выразить свойство то, что модуль, конечно, представленный, ну, в терминах как сохранения каких-нибудь там пределов. Ну да, ну в общем это надо будет сформулировать и доказать, потому что он перестановочен как раз с этими с прямыми пределами. Home из него перестановочен с прямыми пределами. То есть такой категорная характеризация конечно представленных модулей. Вот. Ну такое можно сделать для конечно порожденных. Ну, это там всякие интересные приложения имеет, там можно всякие теоремы Морита доказать, я тоже хочу это сделать. В общем, такие планы. Закончить инъективные, поговорить про вот эти конечные объекты, эти теории Морита, и сформулировать хотя бы план доказательства теоремы Митчелла. Я думаю, что это
Какой теорема?
Фрейда Митчелла.
В следующем модуле уже.
Ну, тут займет, наверное, как минимум 2 лекции следующего модуля.
Точно, модуль заканчивается.
Да, сегодня последний занятие.
Следующей неделе вроде не
Точно.
записаться.
Да, а потом начнем всякие резольвенты, производные функторы.
Кстати, вопрос более житейский. А когда мы тёрк пишем?
Ну, ровно через неделю в это же время.
В это же время?
Да.
У нас 3 часа, да?
3 часа, да.
А он как контрольная будет по духу или
Ну,
что?
да. Только, времени в 2 раза больше, значит, в 2 раза больше.
2 контрольные.
Да, как 2 контрольные сразу.
Сейчас. Времени все-таки не в 2 раза больше.
Ну что, вы хотите 8 задач?
Нет. Не, а сколько задач будет? 6?
Ну, я еще не составлял, посмотрите, какие будут задачи по сложности. Там,
Надеюсь, они будут скорее как во второй, чем как в
там есть такие задачи, что можно 2 дать, и нормально будет.
Нет, такие не надо.
А очень опасно.
Сказать, олимпиадные задачи по теории категории не готовы решить.
Что интересно, кстати, теория абелевых категорий вполне себе живая. То есть,
Спрашивают еще, будет ли, можно ли онлайн писать на терм.
Можно.
Такой, да?
да, как контрольный все то же самое. Кстати, по поводу ответ на вопрос, который меня спрашивали в прошлый раз по поводу леммы, вы спрашивали, как там два мономорфизма и, в общем, почему там все работает. Там, на самом деле, если подумать, там получается такая ситуация. У вас есть x, y и снова x, и у вас есть два мономорфизма. Да? Если посмотреть, что там получается, то эта композиция будет тождественная. И этого достаточно, чтобы сказать, что на самом деле, что это изоморфизм оба. Ну, понятно, да, если у вас есть GF1, то надо что-нибудь там сильно скомпозицировать, например, если на F. На G, может быть. G, да. Тогда G у нас мономорфизм, и F уже будет. А вот это там действительно реализуется. Ну, как и было, простое замечание без вычисления дополнительных.
Это первая задача.
Нет, это вопрос был по лемме. Там, помните, была лемма, что ядро А и К представляется в виде суммы ядер. И там мы доказали, что есть два мономорфизма, и по вопросу, почему на самом деле они не просто мономорфизмы, а изоморфизмы, ну, вот по такому простому аргументу, потому что если подать на композицию, это будет тождественное отображение. Ну что, начнем семинар. If I remember correctly, we haven't finished the problem about the map and two sub-objects, like the last problem from the previous seminar. Do you want to see the statement of the problem?
Yeah.
So we have a map, and x prime is sub-object in x, y prime is sub-object in y. Then apply f to the pre-image of the y prime, take intersection with x prime, and this is f of the x prime intersect with y prime. Здравствуйте. Можно, можно даже выйти.
Я, собственно, чего хотел бы спросить. Меня, к сожалению, скоро кладут на операцию. Хотел сказать спасибо докторам.
Ну, на следующей неделе, получается, да.
Это,
Ну, в смысле, ну, как время лекций,
то есть 28 числа, получается.
ну, следующий вторник, я не помню число.
Сегодня вторник,
След-
21.
Да, следующий вторник, вот как обычное время, да.
О, так это получается не только с этим, но еще и с логикой накладывается. Я хотел спросить. Видит Бог, мне такая ирония, что я на прошлой неделе вам по поводу гриппа писал. На позапрошлой неделе по поводу гриппа писал. Что мне это не нравится. Но ситуация такая, что как раз 28 числа меня должны отправить на 3 или 4 дня в больницу на операцию.
Угу.
Если нужно, опять-таки, предоставить там.
Ну, я вижу, что у вас какие-то документы есть, детали не очень важны. Ну,
И
и что?
я хочу что-то сделать, мне нет желания пропускать все работы. Я могу что-то сделать, как-то вот эту ситуацию.
То есть вы уже там 28-го, вы условно, примерно там утром ложитесь в больницу, и вам уже не до этого, да?
Да, примерно так.
Ну, можно придумать такой вариант, что если вам просто пришлют мидтерм в понедельник на 3 часа, то через 3 часа вы мне его пришлете обратно. Но только тут как бы большая просьба, конечно, ни с кем ничем не делиться.
Да, наверное, так можно. Не, ну, конечно, нет.
Ну, потенциально можно и в воскресенье, ну, можно даже и раньше, наверное, если это важно, там, в субботу.
Хорошо.
То есть напишу, можете написать мне в Телеграм, когда вам будет удобнее.
Хорошо, то есть, ну, вы имеете в виду до этого?
Ну да. А вы хотели после?
Ну, я просто исхожу, просто я постоянно хожу на какие-то мероприятия, связанные с каким-то, вот буквально только что приехал из больницы. Мне это, поэтому если фантазии было бы, конечно, мне удобнее писать после, чтобы я мог тоже к этому чуть лучше подготовиться, но это исключительно вопрос удобства. Если
Это просто как бы обещайте, что не будете смотреть задачи, которые были на мидтерме. Если вы мне это пообещаете, я вам дам те же самые задачи, чем через 2 недели. Ну, хорошо, тогда вы просто напишите. Ну, конечно, я там, не знаю, для вас приезжать не буду один, я все равно разрешаю всем пользоваться, поэтому я просто пришлю по e-mail на 3 часа, через 3 часа вы мне вернете.
Я не хочу как-то этим злоупотреблять, поэтому если я, например, не 28-29 классе, я абсолютно... Ну, тут еще нужно будет с логику трясти, потому что...
Ну, нет, это возможно. Просто я не хочу составлять там для вас другой экзамен, потому что, во-первых, это довольно тяжело, потому что задача довольно индивидуальная, а во-вторых, он может по сложности оказаться неэквивалентной тому, что было у всех остальных. Потом довольно тяжело, в общем, угадать, чтобы сложность была одинаковая.
Хорошо, я вас понимаю. Хорошо, ну, я готов.
В общем, возможность есть. Да. Вы напишите, когда там будет удобно.
Хорошо, спасибо большое.
Угу.
Спасибо большое.
Хорошо, до свидания.
Can I try to propose something?
Sure.
About, first I have such diagram. So this is pullback is by definition. This is also pullback by definition.
Угу.
This means that this is pullback. Let us define this A. And let's do such diagram. So we proved that this is pullback, and we want to show that this is pullback. It's the state.
Yeah, so, yeah.
Yes,
So we-
because this is.
Yeah.
So it's enough to show that this is pullback and it's equivalent condition. Yes, we know that this is pullback and we want this is pullback if we know if this is pullback.
Can you please, once again, state what you're trying to prove?
Is it true or not? I claim that we have if this is pullback, then these two are pullback. It's equivalent. If we know that this is pullback, is it true?
Well, I think it's true, but we haven't proved this. Right? We only proved in one direction. If the two small squares are pullbacks, then the rectangle is pullback.
Oh, okay, but I thought no, but and is it clear that this is pullback? I think.
Well,
Uh,
I don't think this is clear. I think it requires proof.
Yeah, it requires proof.
Определение так нет.
No.
this is embedding.
Oh,
Definitely some explanation is needed here.
yeah. Because the images are not defined in terms of pullbacks. Images are defined differently. But I like the first diagram with two pullbacks. This definitely works. Maybe you can just derive the formula just from the first diagram. Now, if you think that this is too hard, try to solve a special case. Assume that x prime is just x. No, I know the statements that if you have two pullbacks, then the kind of big thing is also pullback. I don't know a statement in the other direction.
Statement that if right is pullback and all is pullback like that.
Okay.
Он не ушел, ты случайно, где вода, например, не ушел?
Ну, здесь у нас под объекты, здесь все-таки не пушаута. Образ фактора объекта определялся через пушаут.
Такой образ вообще.
Okay, do we have a proof in the special case when x prime is x?
Well, I think it is the hardest part.
Well, I'm not sure that this is the hardest part. Okay, so assume that x prime is x. So then we have a map from x to the image of f, and well, this map is epimorphism, and the embedding of the image into the y is a monomorphism. Right, and also inside y we have y prime. Well, if you take this first pullback, we will get the intersection of the y prime and the image. And if you take the second pullback, we will get f inverse of the y prime. Right? Since this composition is still just the map f. Okay, now if we go back to the lemma 1, I guess we can say that this is an epimorphism. So since this is a monomorphism, this is also a monomorphism. Now,
Again, by lemma
well, the lemma is saying that if you have a pullback, this is monomorphism, then this is also monomorphism. If this is epimorphism, this is also a push out, and this is epimorphism. Okay, so now we want to understand on our special case, we want to understand just take this sub-object in the X and what's the image of this sub-object. Right, so I want to understand the image, say, of this map, since this is just an embedding. I can as well just understand the image of this map. But this is epimorphism, and this is just an embedding as a sub-object. So what's the image of this map? Just this thing. So that's the proof.
And how we use lemma 1? Because there are many conditions and I can.
Well, there would definitely condition that if you take a pullback and you have a monomorphism, then this second map is monomorphism.
You know that pullback is which one?
No, say start with this one. So this is monomorphism, then this is monomorphism. Then apply the same for the second pullback. This is monomorphism, then this is monomorphism. Now, for the second pullback, we also need, this is epimorphism, hence this is epimorphism. Oh, there was a statement about co-kernels and kernels, so if one co-kernel is 0, then the other kernel is also 0.
I think I can do the general case.
Okay.
Well, as was noted here, actually, yeah, we denote this thing by A. We have, in general, the following two pullbacks.
Mm-hmm.
This map is F. It's just the image of Fi. So we can apply the previous case with the map x prime Fi.
Mm-hmm.
Yep, and here by because this rectangle is a pullback, we also know that this is Fi inverse of phi prime.
Mm-hmm.
So we are reduced to the previous problem.
Wait, what? I would say it differently. Well, we need A to be this thing, right?
Yes.
And so I would say that just by looking at this pullback, you can say this intersection of this and this. And that's exactly what we have here.
Yeah, but,
And, that-
but on the other hand,
And there is also prime missing here.
yeah, sure. But on the other hand, if we
Yeah, and on the other hand, yes, this is also correct. Yeah.
but to apply the previous part that you proved,
Mhm.
we need the following presentation. Yeah. I guess it's clear.
Yeah. Okay, so next problem. So let's prove modular law for abelian categories. So we have a situation where x prime is a sub-object in the x2. This sits inside some object x, and there is object x3 in the x. And then we have the following. You take intersection of the x2 with the sum of x1 plus x3. This is isomorphic to the x1 plus intersection of the x2 and x3.
Еще модулярно называется.
Should this statement be familiar?
Hmm?
Should this statement be familiar?
I hope so. Well, I think something like this you might have seen in the first year geometry and linear algebra for vector spaces.
Это что-то вроде лемма бабочки или что?
No.
Такой сумму вообще
Well, we define the sum in the following way. We have two objects, take a direct sum. Well, these are sub-objects in the x. And then there is a map from the product to the x. And this factors through the image, and the image is the sum. So what is the main relation between intersections and sums?
These are kernels of.
Oh, these are just definitions. These are definitions. Well, you take the say two objects. Intersections sit inside the direct sum, and the quotient is just the sum. Right. So this is the most important relation between these two things. What if you just try to do this for pairs, for say x1 and x3, x2 and x3, arrange them together, use 3 by 3 lemma.
But you can just consider the sum, like three sums, x1, x2, and x3, and then like just take quotients.
Yep,
like
that's something like this you can do, yes. Now in my computation, the direct sum of x1, x2, and x3 is in the center of the 3 by 3 diagram. No, we can forget about the sum, take just one object. Is it true that the intersection of all subobjects containing the given subobject is just this subobject? Well, yeah. Yeah, and then you want to take two subobjects and you take subobject containing the one, containing subobject containing the second, and then take the intersection. Yeah, but how this is different from what I just said, which is a trivial remark, if they simultaneously contain, I mean not the sum, but just contains x1, contains x2. Mm-hmm. Yeah, I think this might be true. I definitely don't use this in the proofs, but I think it's true. No, maybe again by the trivial reasons, like for vector spaces, among those subspaces will be x1 plus x2, right? Well, one of such subspaces that contains x1 and x2 is just the sum.
Yeah.
So, yeah, so we want to show that the intersection of all of them is just this thing. So it is contained in this thing, and if you take the intersection, x1 is in the intersection, x2 is in the intersection, so the sum has to be also in the intersection. So I think that, yeah, this is true, yeah. Okay, I think I want to give you some hints. So let's start with the intersection of the x2 and x1 plus x3. Well, as any intersection, this is mapped to the this thing, right? Yeah, and the quotient by the intersection, well, this is just the sum. So this is x1 plus x2 plus x3. Okay?
Yeah.
So we have this part. Well, what if we keep this x2 summoned? Now we have the sum of x1 and x3. So write x2 direct sum with x1 and x3. Well, there is a canonical map here, well, which is just the identity on x2 and the canonical map from the direct sum to the sum. So this is still epimorphism. Yeah, so the kernel of this thing, for example, is also easy to understand. This is just the intersection of x1 and x3. Right? Now think about this way. Put x2 equal to 0. Then this is definitely true, right? And then this is just a sum of two short exact sequences. One is for x1 and x3, and the other one is just 0, x2. This is the identity, x2. So this is the short exact sequence. The sum of two such short exact sequences give you this middle row in the diagram. Okay.
Why is each kernel x1
Hmm?
Why the kernel is x1 x3?
Oh, again, the explanation is the same. If you don't have x2, then this is clearly the kernel. So you get a short exact sequence with the intersection, direct sum, and the sum. And then take this exact sequence without x2 plus this exact sequence with x2, the sum of two exact sequences. So here 0, x2, x2, and the identity. Okay. So how we can continue this computation and guess some other terms in this diagram? Well, we can.
It's quite easy that we need on the top the second sum.
Here?
Yeah, here.
Well,
Because you have some isomorphism, right?
yeah, I want to notice that here this sum of x1 and x2, x3, since x1 is a sub-object in the x2. Well, if I just remove x1 from this sum, I still get the same thing. So I want to say that I won't take the x2 plus x3. I want this map to be just an isomorphism, and I want 0 here. So this is the map to the 0. So this is what I want as my result. So now I want to understand how I can get x2 plus x3 as the quotient of this object. Yeah, so take x1, direct sum. So, and here we have intersection of the x2 and x3, right? Well, and here we can take definitely the intersection of all three of them. Then there is a map here as before. So this is a monomorphism. Now, again, by observing that x1 is sitting inside x2, here, that we don't know yet. For this we need 3 by 3 lemma. So let's look at just this thing. So this is sub-object here, and this is an isomorphism, right? Again, x1 sits inside x2. So this is an isomorphism. So now, I guess by the standard argument, you can induce map here. Well, you want a map on the kernels, right? So you want to see that. So if you want a map to the kernel, you want to see that. Well, you start here, and then you go like this, and you get 0. Since you can go also like this, and this is 0. So there is a map on the kernels. Now what we see here, this column is exact. This column is again exact. So this is exact. This is exact. This is exact, hence this is also exact. And the exactness of the first row is precisely the statement that we want to show, right? Because on one hand, this is this thing, and if you just directly take the quotient, this will be the x1 pass this intersection.
So again, if we directly with the quotient,
This thing. What part? Well, do you agree that it's clear that all the columns are exact and these two rows are exact? So then I can conclude that this row is exact. So it means that the co-kernel of this map is this thing. So on one hand, this is this part of the formula. On the other hand, if I just compute this directly, this co-kernel, I'll get this part. That is because, well, this is two sub-objects, and the quotient by this thing is supposed to be their sum. So their sum is x1 plus the second sub-object. Okay. This is necessary pain. I'm going to need this later. And here is a fun exercise. So let A be AB5 and AB5 star. Show that A is equivalent to 0.
is there like an easy way to memorize what is 85 and 85 star? Because is it about
No, first of all, you don't
direct
need, you don't need to memorize stars, because stars is just to go to the opposite category.
Yeah.
Yeah.
I really don't want.
Well, it's I think it's I don't know. When I first time saw these conditions, I think I immediately memorized all of them without because it's just such nice and kind of reasonable conditions to put on a category. You don't need any motivation explanation why you want these conditions.
Well, and in the definition it says AB5 is a category that AB3 category, and since some conditions of previous theorem are satisfied, it's the,
Yeah.
you know,
Yeah, and by the way, if I'm not prepared for this course, you just randomly find me in my room, say a year ago, and ask what is AB5 category, I would give you a completely different definition that we don't cover in this course. Because for me, the most natural definition is that the filtered colimits are exact.
wait, so this is equivalent to,
Yeah, so that would be equivalent. And we started with a small condition that intersection with one object commutes with sums.
Yeah.
This can be generalized to the pre-images by the map straightforwardly. And the non-trivial generalization of this condition was that the direct limits are exact. If you have a short exact sequence of objects, apply the direct limit, you still get a short exact sequence of objects.
А тогда АБ с чертой это про то, что обратно делают на, правда?
Да.
мы индактив.
Только не АБ5 с чертой, а АБ5 со звездочкой.
When you say like take an exact sequence and apply everything to it, do you mean that there was like a direct system of exact sequences?
Yes, exactly.
So again, the category is AB5 and AB5 star. So if you have some, let's say, exact sequence, right, short exact sequence, then we can apply limit directly. And,
Yeah.
and
Well, to be precise, you need to say that you have a directed system of short exact sequences, or a projective system of short exact sequences. You apply the limit to the first and the direct limit to the first and inverse limit to the second, and you still get an exact sequence. But you won't need this in this generality. Well,
Maybe.
I never saw that anybody tries to talk this way about these categories, but well, the problem is it's that the sums, if it go to the opposite category, it will be something different.
Yeah.
It won't be just intersections.
That's why I'm generally asking. You said we don't need it, but somehow I guess we need some conditions on AB5 star. And I just don't know any other conditions other than about projected width. So I guess we'll need it.
Well, still, it's possible to give a proof without thinking about these conditions. We need just a little bit from the AB5. By the way, is it clear that any AB5 is AB4?
I think I asked in the previous lecture, you said that it's an exercise.
Yeah, but how to do this exercise?
Well, I haven't done it.
First part of solving the exercise is remembering what AB4 is.
Ну, потому что если
AB4 is about
co-products are not
which,
exactly given.
COVID, sorry.
Yeah, co-products are exact, yes. If you know that direct limits are exact, can you derive that co-products are exact?
Well, I guess you can consider some families of index subs. Well, yeah, I think we had this argument
Yeah.
that you can
The- Yeah, the observation was that if you want to take a co-product for some family, you can present this as a direct limit of the co-products, say xi, now I is in J, so this is I is in large I, and J is subset in I, and it is a finite subset. So this proves that AB5 implies AB4. So indeed, all the conditions are stronger, stronger, and stronger. So if you have ABN, it implies ABN minus 1. Yeah, I think you also last time you asked the question, what would be an example of AB4 category, which is not AB5, AB3? I think it was your. Well, the example is the category of sheaves of abelian groups, and then you take the opposite category.
Sorry, what category?
The category that is AB4, but not AB3.
Yeah, what is
You take sheaves on a reasonable topological space. I mean, the topology is not discrete. A sheaf of
I
a,
just take standard Zariski topology on R.
I think this works. Yeah.
Okay.
Yeah. They take a category of abelian sheaves and take opposite of this category.
What is wait, why is it not?
So it's AB4, not AB5.
No.
No, I think it's AB3, but not AB4.
Why not AB4?
Well, exercise. If you know something about sheaves, you can probably do this.
So if we go back to normal category, it says that it's AB3 star, but it will not be AB4 star. So
Yes.
it has limits, but they're not exact. But products are not exact.
Yes.
Well, yeah. Oh.
Products are always exact on the right. Yes.
On the left. No, products are limits commutes with kernels. So on the left.
Yeah, left exact is the preserved.
Oh.
Yeah, so because kernel is in it.
Yes.
Yeah, so
So exactness on the right is not true. Oh yeah, that tensor product, yes, is the right exact and the whole. And what you want to compare this with the home? Yeah, left exact, yes. No, I don't see a contradiction. Well, anyway, let's do this exercise about categories. Well, maybe to give you some additional motivation, we can derive the following corollary from this exercise. Suppose you take R modules, take the opposite category, and assume that this is category of S modules for some other ring S that you can construct from R. If you just look at this exercise, what you can say about this situation? Yeah, in this case, R is 0 and S is 0.
How do we construct S?
No, that was a hypothetical construction. Suppose that the opposite category is again the category of modules over some S. Well, this is not possible because then the category of S modules is AB5 and AB5 star, so 0 category. S is 0, R is 0.
Yeah.
Here they are equal, not equivalent. Here we need not equivalence, but that these modules are equal.
No, that's an equivalence of categories. So if one category is equivalent to another and one is AB5, then the other is AB5.
Функторы, которые эквивалентны с категориями, все равно эти сохраняют, это очевидно, да?
Yeah, I guess if you have an equivalence, that what's the left adjoint and the right adjoint for the equivalence?
So,
Yeah, so, well, I mean, what's important that what's important that this is left adjoint and at the same time right adjoint, and right adjoints preserve limits, left adjoint preserves co-limits, so they preserve everything, in particular they are exact. Yeah, and also I'm saying this without a proof, but R modules is an example of AB5 category. In fact, this is an example of a Grothendieck category. So, one more exercise that you can do.
I'm sorry, and what is that theorem that we are apparently not going to prove, but it's very strong that you wanted to prove?
Well, the Freyd-Mitchell embedding theorem.
Yeah, yes.
So that for any abelian categories, there is an exact, fully faithful functor to the category of R modules.
Fully faithful. So you can embed every category in
In R modules, yes.
wow.
No, we actually need to be a little bit more precise when you state this. Well, This definitely works if the category is small, but in applications we don't want small categories.
You mean when the objects not on one set, yes?
Yeah, so that might be a problem.
But these kind of problems, we don't really look in this course, right? Like at all.
Well, if they are reasonable problems, we definitely look at those problems. For example, today we wanted to understand that we take a coproduct over a set, not just a class. That was a reasonable thing to do.
So EB star, 5-star condition, it's we change sums to intersections.
Well, I was saying that I'm not sure that this would be a correct condition, because in the opposite category, if you have sums in the category, in the opposite category, it's not intersections.
Yeah, I think you need to assume projective.
What you really need to do is this argument that AB5 implies AB4. You can present coproducts, and then you.
Уже рабочие со звездой плохая.
Какой вопрос?
Just put star, it's obvious that we can put stars, right?
Если АБ4 и АБ4 со звездой, то оно уже ноль?
Нет, почему уже нет? Ну, модули над любым кольцом такие.
And if AB5 and AB4 star.
It's still not enough.
Well,
Well, again.
I don't really see much use in it.
If modules satisfy AB4 star,
Yeah, okay, yeah, I understand. But I just want to avoid that giving any conditions on AB5 star, because they seem to be kind of.
well, for AB5, give you a way to present coproducts as directly limits, right? AB5 star give you a way to present products as inverse limits. And then you use that use something.
Could you please explain what you said last sentence?
Well, maybe I just give you a more specific hint. As a starting point, can you show that, you take coproducts for some family of objects, then there is a canonical map to the product of the same family. Show that this canonical map is an isomorphism.
In the case when AB5
Mm-hmm.
Easy, right? Because for finite, they are both just the multi-product. They direct
Byproducts, yes.
Yeah, byproducts, but many of them. And since taking limits and incolimits preserves exactness, where not?
Yeah, I would say that, for example, that argument that we have here shows that AB5 condition give us the injectivity, the monomorphism, and dually AB5 star give us epimorphism. Hence, this is an isomorphism.
So again, the proof just says that we have this for the finite, right? And then you just take the limit, and limit preserves this short exact sequence. I guess you want to write zeros on the left and right, right?
I'm not sure that this is the correct
Well,
proof.
my idea was like that. So
Yeah,
we
yeah.
take an isomorphism, which we know to be an isomorphism when indexing sets are finite, and take limits.
Yeah, well, the part that I don't understand, take limits, and also you need to take the direct and inverse limits.
and what's happening?
And why not? We have those.
Well, this is the reason why I want to separate this into two different observations. If you start just with AB5, you get that this map is monomorphism, right?
Yeah.
Since
Yeah, I
in,
see.
since well you have this formula, and the direct limits preserve monomorphisms. So this will be a monomorphism. And then just do the dual argument. You present the product as an inverse limit of such things. And since we have AB5, the inverse limit of epimorphisms is an epimorphism. Hence, this is an isomorphism.
Sorry, what's one map?
Hmm?
What's this morphism?
Well, do you see this natural morphism that we always have?
We have morphisms from side to
It's induced by
I see natural from product to
Push the addition from product, там тот же самый аргумент будет просто в другую сторону.
Сейчас, я вам сейчас сделаю вообще не понимаю.
Well, we proved one preliminary step that we have isomorphism for any set of indices.
So we are not done.
Yeah, so this is just a simple observation.
No, but this has to be bad because if you just take xy, right, and assume co-projection and projection, then we'll get the projection. Oh wait, no. Yeah, we'll get that the composition of projection and co-projection is in isomorphism.
Why?
Yeah, because we don't know the.
No, you'll get just something which is isomorphism in the middle, then you have projection and co-projection.
Yeah, I agree. It's not. Yeah, we need the arrow in the opposite direction to actually see something.
You mean that the left part is direct sum and that's why what's this morphism? I can't see.
Well, you want to specify a morphism to the product, right? If you want to specify a morphism to the product,
Yes, two exercise.
yeah, so what do you see maps from the coproduct to the x's?
You mean
Well, and to specify map from coproduct to xi, we need to specify map from xj to xi.
Mm-hmm.
But we don't have the maps from the coproduct to xi, like natural maps.
В смысле,
No, we have.
по всему, кроме этого. А поэтому
And now we have. Okay. Well, that's weird. So it has to be bad for some reason that we have these maps.
Yeah, for example, look at the R modules. If you have such an isomorphism, that's already a contradiction.
Well, yeah, of course, if we have an infinite product and coproduct, yeah,
Mhm.
we can, it's not isomorphic.
But for abelian categories, we need to work more. It's not immediately clear that this gives us a contradiction. of some object X? That might be a good idea, yes. And might be a good idea just to consider, say, countable product. It would be enough to get a contradiction. Say, product over natural numbers of X with itself. Another little but important remark. Is it clear for you that any growth-antic category is complete? Any growth-antic category is complete. Well, we have growth-antic category. Then any such category is complete.
First, we have to solve finding every category.
No, definitely remember what it means to be a complete category.
It's something about
It's 85 with a generator.
Yep.
well, 85 means 84.
94 means 83.
Yeah, but this AB3 is co-completeness.
Completeness. Okay.
So growth-antic category by definition is co-complete, but it is also complete.
Because it has generator.
Yeah, that's a right observation. We proved a general theorem, maybe opposite of this theorem. If when you have a complete category with a cogenerator, then this is actually co-complete. And that's is in some neighborhood of the discussion about the special adjoint functor theorem.
So we have the dual statement.
Yeah, so here we apply the dual statement and get that any growth-antic category is not just co-complete but also complete.
Say something nice about.
No, this is just a remark that I just think that you need to understand this. I never mentioned it on the lecture. It's not helpful to solve the exercise. Now you take growth-antic category, which is AB5 plus a generator, then this category is automatically complete. No, no.
Don't we need 85 then? Only generator?
Yeah, but we have AB5.
Ah,
It's part of the definition of a growth-antic category.
окей. Вы просто сказали, что кополный плюс генератор, значит полная теорема.
В теореме, да.
Там будет правильно.
Да, там и невозможно сформулировать даже, там понятия точности не было.
У вас есть, по-моему, уже время вышло, да?
Do we need to use maybe 5 and maybe faster conditions anymore, or is
No, I think the rest is just straightforward computation.
Там сделать отображение искового текстового зата и потом зата в XT. Там чистая ерунда, но мне не говорится здесь.
well, I thought the following. Suppose we have an object with more than one element.
Okay.
So I want to arrive at the contradiction. Consider the isomorphism of countable product of X with itself, countable product of X with itself,
Mhm.
and consider whole. Well, which functor this thing represents and computed on X. So whole from X to product, it has cardinality at least 2 to the power of n.
Okay.
But I can say I weren't able to say anything nice about morphism from X to product of X with itself.
No, because it's not possible in general. Да. Я не помню, на лекциях это было на семинаре, но это было так или иначе. Я думаю, это на семинаре была задача, мне кажется. Ну, мы использовали наблюдение, ну, по крайней мере, то, что я предложил, наблюдение, что копредел — это правый сопряженный к дельта, а была эта теорема Сафт, которая давала гарантию существования правого сопряженного, из этого все следовало.
Да, может быть, это даже семинар.
Да, я думаю, это была задачка на семинаре. So it looks like it doesn't make any sense to leave exercise to you because you don't do anything anyway. So I can as well give you a solution. We'll take an object which is just a finite, say, product, embed this into the countable product. Hmm? Well, let's take product. Maybe we can do this for cop. Yeah, so it doesn't really matter. So here we have a quotient. So that's a short exact sequence. And this works for any n. So then we can take the diagonal map, right? And form a pullback. So here we get delta inverse of the x to the n. Now here I have a projection Pn plus 1 to the x. So the composition of the delta and Pn plus 1 is the identity on x. Right? So this whole composition is the identity. Well, what else we can see? We can see that if I take this projection and take composition with this embedding, I'll get 0. So in fact, this is a map on the quotient. So let's call this Pn plus 1 with the bar. So, and let's take this quotient map Q. So now the identity looks as follows. I have delta as before, and then I apply Q, apply Pn plus 1 bar, and this is still 1, right? So I can see from this that the composition of the Q and delta is a monomorphism.
Yeah.
So since I constructed this retraction. So this composition is a monomorphism. By lemma 2, this thing is the kernel of this. So delta inverse of the X from the diagram lemmas. And I told you that's very useful lemma. So this is 0.
I mean, what does it state?
Well, the statement was you take a short exact sequence, take a square, this is a pullback, if and only if this thing is the kernel of this composition. So,
Is it about that you can replace something there, right? And make it short exact? Because I think it's something like that.
well, I look at this short exact sequence. So then I take the diagonal map and take the pre-image of the subobject under the diagonal map. In other words, I just took a pullback here. On the other hand, I have projection, which index n plus 1. So then this composition is the identity, and also this composition is 0. Since this composition is 0, this map can be lifted to the quotient. So hence there is this map. And now I just look at what I understand. So this composition is 1, and I can rewrite this map as the composition of these two. I'll get this, and then I can conclude that composition of these two maps is a monomorphism. From this observation. Well, if it's just a general thing, if you have f g is equal to 1, right, and you take a composition, say g with some t, and this is 0, you want to show that t is equal to 0, you take a composition with the f, this is 1, so t is 0. Okay, so for any n, such pre-image is equal to 0. Now,
This is because Q is mono and this thing is exact, right? Like,
so this is mono. By lemma 2, it means that this is 0.
yeah.
Okay.
Okay, yes.
But we haven't used anything up until now, right?
So far we haven't used yes.
Okay.
But I haven't finished the proof. Well, maybe what you want to derive from this, that x is actually 0, right? So we have only this observation. So how you can derive that x is 0? There is an additional step. Maybe you can think about this for a second.
Well, we should take
What limit?
well, if xn, if m is greater than n, then xn embeds into xn.
Mm-hmm.
Now, then delta inverse of xn embeds into delta inverse of xn.
Well, I think you're making this much more complicated than necessary. Oh, wouldn't this be correct if you say that x is the pre-image of this whole product?
Потому что это же компатибельная штука, и там просто получается 0 короче, 0 везде. Не выявилось, извините.
No, so far we only get that this is 0, that this pre-image on the diagonal map is 0. But do you agree that x can be presented this way?
And now we use this is over.
Yeah, now we can replace the product with the coproduct.
Okay.
Okay. So, but this coproduct can be also replaced with the sum. So clearly the image, which is this thing, is equal to this thing, since this is just several copies of the same object. So we have this replacement. Now,
We proved that sums and inverse images commute? No, we didn't.
sums and inverse, well, you don't need this here. You just go to the very first theorem that I proved about AB5 categories, that the pre-image of the sum is sum of pre-images.
Well, that's what they said.
Yeah. So then you get this thing. Yeah, I think even better, here you can write this as the sum of the xn's. And all these things are 0, so x is 0. Okay. So we have a break for 2 weeks and just some silly exam next week. There will be 6 problems like this on the exam. There will be 5 or 6 problems like this on the exam next week.